So the variable attenuator provides an attenuation by varying the degree of insertion of a mass resistive strip to the waveguide. Okay, so now we will go to the fixed attenuator. Fixed attenuation means just like it has been used as a resistor in a DC circuit or AC circuit we use in previous circuit labs when we connect resistor, inductor or capacitor. So resistor is an impedance, but here impedance came through to the attenuation of the signal. So there are two attenuators, variable attenuator and fixed attenuator. The fixed attenuators is to provide a fixed attenuation at 20 dB, 20 decibel. The attenuation is obtained by insertion of a straight portion of standard waveguide. It is a straight portion of standard waveguide and it has been used as an attenuator, fixed attenuator. This is the figure of directional coupler, and you know the directional coupler allows directional coupling of energy. That means there are two type of energy that go through to there and that go through to straight. So there is some coupling on it. That means some power splitting on it. If there is a power go through to there, some power will split there and some power will go straight to it. So just like that, or vice versa, if you just input the two parts here, it's like in that part and that part, that will totally couple to it and go, some will go through to it and other will not be out through to it, and both will be coupled to each other. So directional coupler is consisted of two waveguides combined together and coupled by holes at the joining section of the two. Directional couplers are very popular in microwave system, where measurements of incident and reflected power that has been used in the incident and reflected power are needed to determine standing wave ratio, that is SWR. The directivity, which is a figure of merit of a directional coupler. So the directivity is the figure of merit, that is one kind of key parameters in directional coupler, is a measure of how well the power can be coupled in the desired direction in the neighboring waveguide. Usually you can see here there are two rectangular waveguides that's been joined by a bend of the waveguide. There are two waveguide sections in that input section, and there is a single path that go through to the other section. So usually one end of the neighboring waveguide contains a matched load which absorbs the energy headed towards undesired direction. The directional coupler used in ED3000 has a coupling factor of 10 decibel, that means plus minus 3 decibel, and a directivity of 40 decibel. A directional coupler is represented by a graphical symbol of the following. These are the symbols, these are the graphical pictorial representation of directional coupler. Now go through to the slotted line, the next measurement device. In measuring the standing waves inside a waveguide, so when you have to measure the incident wave and reflected wave, so you need to use the directional coupler. Okay, so keep on mind which measurement tools are using to find out which thing. Okay, if you want to find out the standing waves, so you have to use the slotted line tool, that is a slotted line tool. Okay, so in measuring the standing waves inside a waveguide, a slotted line is used to probe the amplitude and phase of the standing wave pattern. Obtaining the standing wave pattern information allows us to determine the wavelength, standing wave ratio, and the impedance of the transmission line. As the name implicates, a slotted line has a slot along its center. So there are some slots under this section, and for the central line of the broad side of the wall, there are some broad side of the wall. There is two walls in that rectangular portion. This broad side of the wall has some slots. Okay, So that is known as the slotted line. An assembly consisting of probe and a crystal detector is designed to slide along the open slot, and as it does, the probe sample the field in the waveguide while the crystal detector provides rectified signal. That is the crystal detector section that provides the rectification of the signal. The depth of the probe into the waveguide is adjustable. That is the probe, and the depth can be adjustable here. That is the adjustable probe depth. Okay, you can adjust it by just moving the knob inside out, and that can easily get adjusted. And the strength of the detected signal is proportional to the depth. The strength of the detected signal is proportional to the depth. That means if the depth is too much, if it is too much deeper in the slot, you will get a strong signal. Okay, that means if the signal is quite weaker, we just have a depth on it, so it will make it more stronger out of the box. The user should be aware of an optimized depth in use of a slotted line, since too shallow depth would make the detector signal too weak. To deep depth would substantially reduce the main signal power in the waveguide and may even cause field distortion. So you have to keep on mind two things. First of all, you have to keep on mind what is the optimized depth of that kind of particular signal should have to go for. If it is, if you don't know it, so the signal will come too much weaker than you expect. And if you just go too much deep substantially, that can also reduce the main signal power in the waveguide, or may even cause the field distortion. It can also cause the field distortion too. So we have to know some optimized value, that how much deep will go through to the slotted line section. Next, the slide screw tuner. There is a slide screw tuner. Same things will happen through the total waveguide sections are going through to there. You can see that from the previous section to the now, most of the things are related to the waveguide. That is the waveguide section. You can see here, that is the waveguide section. And if you just think there, that is not the waveguide, that is the screw tuner section. And that is you can just tune by just moving this. You just tune it. Okay, you can just tune it there, and the depth of the probe varies. Okay, so that is a slide screw tuner, almost same as a slotted line tuner, but that's used by the screw. So there are some relationship between the probe's depth and micrometer scale. Micrometer scale means the micrometer scale. Sorry, micrometer scale. If you just go 3 millimeter deep in micrometer scale, the probe depth will be 7 millimeters. If it is 5, then the probe depth will be 5. If it is 7, that will be 3. So that is one kind of a ratio, unit versus millimeter. So 3 is to 7, 7 to 3 is the ratio between the micrometer scale and probe depth. 5 is to 5 is almost the similar on it. That means totally it will go through to the 10. But if you go through to the 9 millimeter, that will equally 0. The probe depth, there will be no probe depth at all. So that is one of the things you have to keep on your mind. Now there are a lot of measuring devices. We will go through to it, but these are the basic devices to find out this. And last but not the least, the crystal detector, and that is the main detector side, that is known as the sink of or output of a waveguide system, or you can say that the microwave system, because by this we can accumulate the power and measure, then we can measure the power. Okay, so the crystal detector is the detector, and it is go through, and it is connected to the output side of the microwave system. Thank you very much for being with me in this lecture from first part to second part. I hope you will understand the measuring devices.